Floating point types. Actually, you might have noticed that over of last few lectures we were discussing the basic types, and we were also discussing the internal architecture of the computer, or how those numbers are actually stored in the computer. We also saw how they are converted to binary format and how they are displayed as hexadecimal. And now we want to discuss the floating point numbers, and we are just continuing this topic. The floating point types, we have float, double, and long table. So let me demonstrate that. I think in the last 1 or 2 lectures we have declared and used these type of variables. So this is the basic structure. I'm going to use that. Let's declare a variable float a, and let's initialize it with for example, we just have the value of 247.2, any number with a decimal part, and let's see what it looks like. See out, and then the value of a, and then I write an L. So let's run this code and see what we get. We are getting 247.2. Now what I'm going to do is, actually floating point means that the decimal number actually floats from right to maybe left, and it has something known as a variable precision. We are going to discuss that in the next part of this lecture. But let's see if we can have the set precision. Let's say I want to display a few more digits after the decimal point, even though it has zeros around it. But let's say if I want to use something known as set precision, and I want to have 10 precision places after the decimal point. So if I run this thing, it will probably throw up an error saying that this thing is not defined over here. Actually, I need to include this IO manipulator or stream manipulator header file. So what I'm going to do is I'm going to include IO manipulator header file, and let's run this thing. I want to have 10 decimal places after 247. So this A contains this number. So this number would be displayed at the output stream, or would be sent to the output stream to be displayed on the command prompt output as 247.2.0000, and that is my expectation. But let's run this thing and see what we get over here. So after running this thing, the computer did not store 0.2, even though it's quite straightforward to store 0.2, but it is stored 199969. So, and after that it's probably zeros over there. So what is actually going on, we are going to discuss that in part 2 of this. After I run this code, I want to discuss how these numbers are actually stored. So we will understand the reason why it's not displaying 247.2, or why it's not storing 247.2, but rather an approximation of 247.2. Because in floating point numbers you can have a very large number and a very small number, but due to that extremely large range of numbers you can represent, you have to lose some precision. And if you are losing that precision, you have to keep in mind that the results would not be that accurate. We will be discussing few examples in the later lectures on how floating point numbers can actually have really weird problems if you are not really careful. So let's have another but let me show you what is actually happening behind the scene. I'm going to discuss that in detail. Let me show that. Okay, so if you go to this website, if you just write double IEEE 754, so if you write IEEE 754 you and the Wikipedia entry, you will see that here, let me zoom in there if it's possible. Here, that a 32-bit floating point number. Why is it 32-bit? So let's check the size of operator. C out, and size of A is, and after that let's have an L over here, and let's run this thing. So I think that float is a 4-byte. Here it is 4. It means that C out size of float A is a 4-byte number. 4 byte means 32 bits. So 32 bits, 1 bit is reserved for sine, 8 bits are reserved for exponent, and 23 bits are reserved for are for the fractional part. We are going to discuss what that fractional part is, so don't worry too much about it. We're going to see that. Okay, so whenever we have a double precision, so if I declare a variable such as double, just a name, double G equals to 247.2, same value, but let's have this thing. But now we are going to discuss, we're going to have D over here, and I'm going to have the size of D. I'm going to have a size of D is, and so that it's easier to read. So if I see what the size of D is, I mean, so D is that double precision is actually displaying 247.2 and storing 247.2 as it is, but this 4-byte number is not, and this D is 8 bytes. This is double precision number. So if you look at the structure, we see that 63 bits are now reserved instead of 23 over here. 63 bits are reserved for fractional part, and the exponent part actually has 15 bits, so it can have, I mean, double precision. And there is also known as it has another something known as sorry, I think I displayed the extended precision, sorry about it. So double precision is 52 bits fractional part and exponent is 11 bit fractional part, so that's the double type. Okay, so it's a 64-bit number. And there is another one which is known as extended precision, which we call long double. So long double has 63-bit fractional part and double precision has 52-bit fractional part. It depends on the implementation we are working with. So let's declare another variable and let's call that variable long double, just a name, let's call it B, equals to 247.2, and same thing, going to copy and set precision 10. I'm going to have B over here, size of B is and size of B, and let's run this thing. I think it should be like 16 bytes. So long double has 16 bytes and double has 8 bytes of memory occupied and float has 4 bytes of memory. I mean, these two numbers are displaying this 247.2 and storing 247.2 as it is, and which is doing it rather correctly, but this floating point number is not. So let me repeat what I've done over here. I've declared 3 kinds of floating point numbers: float, double precision floating point, and extended precision floating point, and they have different bits for storing the values after the decimal part. So this thing, let me have it over here. This thing, the 4-byte float, 32-bit floating point or 4-byte float, has just 23 bits for fractional part. The double has 52-bit fractional part, and the extended precision has 63-bit. It depends on what are the implementations. Some compilers might have 12 bytes of instead of 64 bits. Some compilers might have 16 or maybe 12 bytes to store the extended precision. In this case, in my computer, we have 16 bytes for long double, 8 bytes for double, and 4 bytes for float. So in the next part of this video, I'm going to discuss why we have this number, even though we stored 247.2, but it actually stored 247.199969. So let me go to the notepad and I'm going to discuss how this number is actually converted to binary format. Point standard format, IEEE 754 format from this website. You can look it up on internet, IEEE 754 Wikipedia entry. You will see this format. The double precision has more bits for the fractional part, and long double or the extended precision has even more part for the fractional. So what we are going to do is we are going to convert this number, a decimal number, to this. I mean, this is 0.15625 being converted to here. We are going to convert 247.2 to decimal. Before going to that, if you want to take a look at the different floating point books, so this is a very good book, Handbook of Floating Point Arithmetic, with these writers. Just look it up on your internet, you can find it there. It has some really some examples, and we are going to discuss these examples in a future lecture, some of those actually, where if you are not really careful with the precision you are using, you can have some really weird looking errors, because the floating point number can actually represent some really small values and very large values. So to have this extremely large range to be fit inside in this 32-bit number, we have to lose some precision. That's why it's known as floating point. We're going to see why we call this floating point behavior. It has some examples. If you want to run these examples, so instead of this printf and scanf, you will use cout, and for scanf you will use cin. The rest of the things are just like that. I mean, you just run this code for this loop and so on and so forth. We are going to discuss this loop, especially there's this example, the chaotic bank society, and it's a really fun example, but this thing can have some really interesting behavior of what this thing actually does, since if we are talking about some kind of an irrational number, that is the natural logarithmic e. So since we have finite precision, it might have some weird looking behaviors. Okay, so coming back to our example, what I need to do is I need to convert this 247. I need to convert this 247.2 into IEEE 754 format. So this 754 format says that the sign bit is the most significant bit. If the number is positive, this thing has to be 0. If the number is negative, this number has to be 1. So we have to convert this 247.2 to a binary equivalent number. So first part is, so what we're going to do is, the first step is we need to figure out the sign bit. So sign bit would be 0 because the number is positive, so we will just put 0 over here. Then the second part is we want to convert 247, which is in base 10. We just take this part, 247 base 10 to binary. So I mean, there's a really simple way of doing that. We can just write the placeholder 1, 2, 4, 8, 16, 32, 64, 128 and 256. So we just turn on 128, we turn on 164, and when we turn on this 32 and so on and so forth. We know that's how it's done, and we just turn on the bits which is needed. There is another method which is given in your textbook. It is the repeated division by 2. Why we divided by 2? Let's go back to this number. 247.2 is a decimal number, so anything this before at the left side, the placeholder says 10 to the power 0, this says 10 to the power 1, and this thing says 10 to the power 2. The placeholders on the right of the decimal would say 10 to the power minus 1, and if it has some numbers over here, so it will say 10 to the power minus 2, the placeholder would mean 10 to the power minus 3, and this thing would mean 10 to the power minus 4. So similarly, if we have some kind of a binary number, for example 0110 and so on and so forth. So this number, since we are talking about binary, we are talking about base 2, so this placeholder would mean 2 to the power 0, this placeholder would mean 2 to the power minus 2 to the power 1, 2 to the power 2, we just by call 1, 2, 4, 8, 16, and these placeholders at the right of the decimal would say 2 to the power minus 1. Just as this in decimals in some system we had 10 to the power minus 1, this one would have 2 to the power minus 2, and this one would have 2 to the power minus 3, and so on and so forth. So on the right side of the decimal you are decreasing the powers of 2, on the left side of the decimal you are increasing the powers of 2. So we need to convert this 247 to this binary. So there is another method known as repeated division method. So we just divide 247 divide by 2, and we keep track of the remainder over here. So keep track of the remainder, what the remainder is. So coming back to this thing, so 123 into 2 is 246, so remainder would be 1. Just divide it again, and we get 61. The remainder would be 122, so remainder would be 1. 30, divide 61 by 2, we get 2 into 30 is 60, so remainder would be 1. 2 into 15 is 30, remainder would be 0. 2 into 7 is 14, remainder would be 1. So 2 into 3 is 6, remainder would be 1, and 2 into 1 is 2. Sorry, the remainder would be 1, and 2 into 1 is 2, so remainder would be 0, and sorry, I done it incorrectly. So this thing is 2 into 3 is 6, remainder would be 1. 2 into 1 is 2, so remainder would be 1, and 2 into 0 is 0, so remainder would be 1. So we just end where we have 0 over here. Sorry about the mistake. So we go in this direction, so that's the most significant bit. So we are going to write 247 in base 10 equals to 1111 and 0111, and that is in base 2. So we have this number, the whole number part. Now we need to convert this 0.2 in base 10 to binary. So here, since we are not talking the fractional part, then fractional part means that here it was 1, 2, 4, 8, 16, 32, 64. Here it would be 1 over 2 is 0.5, 0.25 or 0.625 and so on and so forth. You can turn on the bits if you need it, but that's kind of difficult. So what we are going to do is, since we have divided these numbers, now we are going to multiply the fractional part. So, and keep in mind that just going to demonstrate over here. So 0.2 into 2, and start with 0.2 over here, equals to 0.4. So that means that just take this number 0. Now let's take 0.4 into 2 is 0.8. Just take this number 0. 0.8 into 2 equals to 1.6. Take this number. So now the remaining number is 0.6. So we have written 1 over here. So into 2 equals to 1.2. Take this number 1. And then we have 0.2 into 2 equals to 0.4. Take this number 0.4, and just right over here, 0.4 into 2 equals to 0.8. Take this number, that is 0. If you can see, we are getting the same pattern over here. So the next number would be 0.8. 0.8 into 2, that would be 1.6. So take this number 1. So next number would also be 1, because 1.6 would into 2 is 1.2, and it will just repeat. So we can write this thing as 0 0 1 1, start and going this direction. Okay, 0 0 1 1, then 0 0 1 1, 0 0 1 1, and this will keep on going forever. So you might have noticed that this thing is a rational expression with a repeating terms. So that means it cannot have 0.2 exactly in binary format. I mean, you might have noticed that if I divide by 3, what do I get? 0.3333. I mean, it has a repeating but an infinite expression over here. So this thing is never equal to, if you just multiply this thing with 3, what do you get? You get 0.9. So that means, I mean, it's just a repeating expression, but you have like an infinitely long expression, then it will equal to 1 over here. But here, if you have a finite precision, you will not get 1 over here. So same pattern is happening over here. So that's why we were getting 247.19969, but I'm going to demonstrate why this happens. So it is a repeating pattern. So what we are going to do is, we are going to write, I need to write this number over here. So this number and this number. So the whole number part, I'm going to write 11110111. Then this part, decimal, 001100110011, and it will just keep on going forever. Then what I need to do is, I need to float this decimal point to here. So let's see, 1 2 3 4 5 6 7. I made the decimal point over here. So I'm going to write it again, 1.111011011, sorry, and then 0011 0011 0011 0011, and this will keep on going forever. Into, since I moved the decimal point by 7 spaces, I'm going to write 2 to the power 7. That's the exponent part. So I have this exponent part is the next part. That's I'm going to fit over here. This thing, the exponent part, this thing is 8 bits, but this exponent part can contain positive values as well as this exponent part can contain negative values. So that means that from the range of 8 bits, that will go from 0 to 55. So that means it would, I mean, in the initial range it will contain the negative values for the exponent had it been a number less than 1, or had it been a number less than 1. So, and here from halfway through it would contain the positive values. So what we need to do is, we need to have some kind of a number which is known as exponent bias. We add this number to this number so that the positive exponent value is biased or jacked up above 127. So the exponent part would equal 7, this number, plus 127. This number is exponent bias. We need to bias the value, we need to jack up the value because we need to fit the negative as well as the positive values from in the same range of 0 to 255. So that means that the exponent part would equal 134. So if I make 134 in decimal to binary. So 1 2 4 8 16 32 64 128. So we had 8 bits, so turn on the 128 bits. 134 minus 128 is 6, so I need to turn on the bits of 4 2, and that's it. We have the exponent part as 1 0 0 0 0 1 1 0, and that's it. What we just write the, and the fractional part, this part is known as the, some other color, maybe this part is known as the Mantissa. We just write whatever bits are there to, whatever bits we can fit without rounding or without truncating or anything. Rounding and truncation does happen, but that's on the topics of some other lecture. We're just going to write these bits as they fit in the 23 bits space. This we do not write because that is understood, and I will demonstrate that if you are converting it back from binary representation to decimal, you just add 1. So the floating point processors and the floating point instructions or the floating point algorithms know how to handle these numbers, and they have some built-in algorithms to take this one. It's some kind of a hidden bit, it's understood to be there. Okay, so coming back to here, so what we need to do is we need to put the exponent part. So I'm just going to copy this thing over here. So I have all the numbers right in front of me, so just paste. Okay, so paste slightly bit over here. Okay, so you might want to draw it in your own copy and so on and so forth. The sign bit would be 0. Let's put a red pen over here. Sign bit would be 0 because we have red pen, because we have a positive number. The exponent part would be 1 0. I'm talking about this number, 1 0 0 and 0 1 1 0. And then we have the Mantissa part, which was this thing. So it is 111 and then 0 111 and then 0 0 1 1. So it's, let's pick another color, 111. Actually it's hard to fit inside, let me hide this. Okay, much better. 111, and then I'm going to write 0 111, and then it's just a repeating pattern of 0 0 1 1 0 0 1 1 0 0 1 1 0 0 1 1. This number represents the 247.2 in IEEE 754 format. So if you want to write it down in hexadecimal, because this is a bit pattern, so we're going to write this number, from here to 1 2 3 4. So we're going to write 0 1 0 0 and then 0 0 1 1 0 0 1 1 and then 0 111, then 0 111, then 0 0 1 1 0 0 1 1 and then 0 0 1 1 0 0 1 1. So we have 1 2 3 4 5 6 7 8. So we have 32 bits over here. You want to convert that into hexadecimal, that will be 3 3 1 2 and 3. The 4 bits represent one hexadecimal number, and we have 7 7 and we have 3 and we have 4 in hexadecimal, because and following the 754 format. So actually this bit stream represents this number. Hexadecimal is used just to represent the number, or just to make the bind numbers much more readable. Now if I want to convert this number back to decimal, let's say I have this number and I want to convert it back to decimal, and I know, and I'm informed that this number is in 754 IEEE 754 format. So that means that the first bit is the sign bit. That means the number would have been positive. Then the next number is these 8 bits are the exponent bit. So I'm going to write these exponent bits as exponent bits, that is 1 0 0 0 4 zeros and 1 1 0. I need to convert it to decimal. So that would be 1, 2, 4. 2, 4, 8, 16, 32, 64, 128. So 128 plus 4 plus 2, that is equals to 134. Since we added 127, the exponential bias over here, now we need to subtract. We need to go in the reverse. So we will subtract 134 minus 127, the exponent bias. We will get 134, we will get the exponent part of 7. So that will be put in the 2 to the power 7 later on, because the formula is actually -1 into sine bit, then we multiply it with 1 plus the Mantissa part, and we multiplied with 2 to the power 7, the exponent part over here. So that's the basic formula to convert it. Now we need to convert. We have figured out the sine bit, that is 0. So -1 to the power 0 would be +1. Then we need to figure out what the Mantissa part is. To figure out the Mantissa part, let me write it down, this Mantissa part, somewhere where we have the space. So the Mantissa part is, let's see, Mantissa part goes from these last 23 bits. So that's Mantissa part is 1110, like 1110, then we have 1110, then 0110, 0110, and then 0110, 011. Okay, let's write it down. So Mantissa part, I'm going to write it from here: 1110, 1110, 0110, okay, and 0110. Let me check. I mean, it's kind of difficult to write. So 1110, that's okay. Then 1110, that is also okay. And 0110, that is also okay. And 0110, that is also okay. So last one is 0110, 0110, 0110, and here is 011. So just write 011. So what we need to do is, in the previous part we actually multiplied by 2 here to convert here, and now we are going to divide it by 2. So the easier way to divide it is actually multiplying with 2 to the power decreasing powers of 2. So here, so this thing here is this thing is 2 to the power -1, this thing is 2 to the power -2, this thing is 2 to the power -3, and it will go all the way to 2 to the power -23. So actually it's kind of a large computation. It's much more likely that computers might have some kind of a lookup table. So I'm going to multiply this one. Let's have some color blue. I'm going to multiply this one with 2 to the power -1. Then let me check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Okay, so you have written 23 bits. Okay, so next is this one would be multiplied by 2 to the power -2. Actually I'm dividing by 2 actually, so it's the decreasing power of 2. So the third one is 2 to the power -3, then 0. I mean, it's not this thing would be multiplied by 2 to the power -4, but that would be just cancelled. This will be -5, -6, -7. So I'm going to write 1 into 2 to the power -5 plus 1 into 2 to the power -6 plus 1 into 2 to the power -7. So this one would be -8, -9. That will be cancelled. It's because you just multiply by 0, so you won't get just as get a 0. -4 is that is cancelled. -5, 6, 7. That's okay. 8, 9 is not included. 10, 11 is included. Plus 1 into 2 to the power -10 plus 1 into 2 to the power -11. So this thing is done. And 11, 12, 13, just forget it. 14, 15. So 1 plus 1 into 2 to the power -14 plus 1 into 2 to the power -15. 16, 17, just cancel that out. 16, 17, 18, 19 is included. plus 1 into 2 to the power minus 18 plus 1 into 2 to the power minus 19, and 20, 21, that's just cancel out. 22, 23 is included, so plus 1 into 2 to the power minus 22 plus 1 into 2 to the power minus 23. Actually, it's a really long computation. Computers might have some kind of a lookup table to to solve this thing for these values of 2 to the power minus 18 and minus 19. After solving using the calculator, I got 0.9312 499,762. So the last thing I need to do is I'm going to use this formula, minus 1 into sign bit. I'm going to use this formula here. So minus 1 sign bit is 0. I'm going to add 1 because I did not include 1 in the original. So if you just remember that we did not include this one over here, I mean that is understood to be there, we just included the Mantissa part, so we need to add 1 here. So the very reverse process actually. So 1 plus the Mantissa part is 0.9312 499,762. Then into exponent part 2 into 2 to the power 7, because this exponent was not 134, we have to subtract the exponent bias to get the exponent over here. So after solving the using the calculator, we got 247.1999969, and that is a value. That means if you store 0.2 or 247.2, the computer, since it has the finite precision, that's why it was storing 247.19969 when we were storing 247.2 as a floating point. So I mean set precision is just displaying the numbers after the decimal point. It's not actually, it's just for the displaying purposes only. So if you just set precision to 1, it will has this value. Let me get that value over here. So it has this value. Sorry, this is from the previous lecture. So it has this value over here. So if you set precision to 1, it will just round it off to 0.2. So let me run this thing again. So that has precision to 1, and just press F11. It will, I mean, so I mean it's 2 e to the power 002. So I mean we are going to discuss that in the next lecture why it's happening. So let's set precision to 4. Actually that's displaying in the scientific format, but you get the idea that if you are saving the floating point numbers in the in the finite space of 32 bits, you will lose some precision for the more range. In integer numbers you have the exact numbers as they are, but in floating point numbers, since the decimal point is floated all the way to the left, we lose some kind of precision when you're storing the floating point numbers. To have more precision, you cannot have infinite precision because the computers have the finite size of memory, and I mean each memory block is a finite size, so you cannot have infinite precision in a computer. And we are going to discuss why. I mean some problems whenever we are dealing, we want to have some higher precision, and we lose when we use some lower precision numbers, we have some kind of weird looking problems. And if you are working in some kind of a machine or some kind of a system which requires extremely high precision, you need to keep these things in mind, that computers has finite precision, and you might want to use some double or long double or the extended precision floating point numbers just to have more precision.